Yeah, good. All right, so quick warm-up. Tangent of 2 pi thirds, of course, is what? Negative, good, because we're in quadrant 2. It's frozen. Yeah, great. Like a butterball turkey. Tangent of 2 pi thirds is negative. There you go, negative. Square root of 3. Very good, very good. Cotangent of 3 pi fourths, also in quadrant 2. -1. Excellent, very good. Secant of 5 pi 6, also in quadrant 2. It's National Goof Off Day and apparently National Quadrant 2 Day. Secant of 5 pi 6. Negative, of course, right? It's a reciprocal of square root of 3 over 2, which is -2 square root of 3 over 3. It's my favorite trig ratio right there. Same as cosecant of 5 pi thirds. What is cosecant of 3 pi halves? -1. Excellent. Said with such confidence. -1. No wavering in your voice. Excellent. So the whole purpose of that blitzing, frenetic unit circle quizzing is so that you have these memorized by heart, or can not forget how to find what they are. All right, so we did meet our last 2 trig functions yesterday. Cosecant and secant, remember, come for free if you remember how to graph sine and cosine, which hopefully you do. So hala and chala, we just make the axis points, vertical asymptotes, and the highs stay high and turn upward, and the lows stay low and turn downwards. All right, so now we are going to quickly sketch these 2 right here. Y equals 1/2 cosecant of -2x minus 1. Now notice it's a cosecant graph, so what we want to do is pretend that it's really a sine graph all the way up to putting the critical values down. But then we'll connect the critical values in a different manner, all right? So here we go. The first thing is to see if it's in standard transformation form. Is it? It is, yeah. Now, if you ever have a negative b value, and we do right here, you don't want to try and graph it with a negative b value in there because it's going to be a little bit more difficult. Rather, use the symmetry, and every single trig function has a symmetry, to somehow get rid of the negative b value. It either becomes a negative a value, the opposite of the a value, or it goes away, depending if the function's even or odd. Cosecant, of course, is even or odd? Odd. And for any odd function, the negative comes up front, and it changes the sign of a. A is currently positive, so now it becomes a negative. It's a lot easier to sketch with negative a values than negative b values. Good question. The only 2 that are even are secant and cosine. Good. It's reciprocal. Cosine and secant are the only 2 even, and the other 4 are odd. All right, so there we go. Let's go ahead and get our little values out here. A, B, C, D, and P, and might as well do R. Again, pretending it's sine. Pretending it's a sine function. So the absolute value of A is 1/2, but it's with a flip. B is now 2, so there are 2 cycles in 2 pi. We're back to 2 pi because we're back to cosecant or sine. The C value is 0, right? So we're not shifting it left or right. That's pretty nice. The D value is -1, so we're down 1. The period is back to what? 2 pi or pi over B? 2 pi. The only ones that have pi are tangent and cotangent. Everything else is 2 pi. So it's 2 pi over B. B, the absolute value of B, is 2. So that's just pi. So the length of a cycle is pi. And the range, the reason we do that is because it does kind of help us when we set up our x and y axis. We're down -1. And then from there we go down 1/2 to negative, if you want to call it -1.5, that's fine. And then from -1 up 1/2 is going to give us to -0.5. So either -3/2 to -1/2 or -1.5 to -1/2. That's the amplitude, right? 1/2 is 0.5. So we're down here at -1 on the sinusoidal axis, and we go down 1/2 unit and up 1/2 unit. And again, that's for sine. That's not the range for cosecant. That's the range for sine, which is why I wrote sine up here. Okay, so it does help us when we're sketching. So let's go ahead and do that. We'll go ahead and with our final graph, and because most of the values are negative, I'll draw my x-axis a little bit higher than usual. we come out the length of a cycle, which is pi. Half of that's pi halves. And then half of that, we're counting by quarter cycles again, is pi fourths. So pi fourths, again, is the most important value on this graph, on the x-axis. Every critical value is pi fourths away. So now over here, we'll have 3 pi fourths, 4 pi fourths. I have room for another, so I'll go ahead and use it. And then at least 1 to the left, I have room for 1 exactly, so perfect. Negative pi fourths. Now we'll get the vertical part taken care of. Here is negative 0.5. And I'll come down here to the bottom and call it negative 1.5. And then right in between there is negative 1. Now, the one thing that I am going to do differently here, I'm not going to draw my new y-axis. If there was a new y-axis, we haven't shifted it, so it's still the y-axis, or my sinusoidal axis. That was just kind of a temporary thing when you were learning how to sketch sine and cosine. But really, it kind of obscures the graph a little bit, and especially since sine is not our final product here. But I'm still going to put the values down as if it were a sine. So sine is Sahala. But because it had a negative a value, remember what happens at the highs and lows? They flip. So to put your values down, you're going to still start on the axis point, which is at negative 1. But now the next point is going to be low. And then axis, and then high, and then axis, and then low. And then I'm going to go back 1, and it would be at a high point. So axis low, axis high, axis low. Negative sign. So you still put the critical values down as if it were a negative sign. But now it's different. We're going to use those critical values in a different manner. We're going to repurpose them. We're not going to connect them with the sinusoidal graph that's continuous. We're going to graph the reciprocal. So what happens is the axis points, not the x-axis points, because there are none for this graph of sine, but the sinusoidal axis points. Those are going to be the ones that become your undefineds. So every sinusoidal axis point becomes now a vertical asymptote. So you draw those first. They become guidelines for the graph. And then the high points stay high and turn upwards, and the low points stay low and turn downwards. So from there, it's pretty easy. And there you go. So having the new y-axis, if there was one, would kind of look like a vertical asymptote. So we don't want to do that. And having the new x-axis on there just kind of takes away from the graph of cosecant here. All right, so there you are. Once you have the graph, then it should be relatively easy to answer questions like, what is the location of a local minimum value? A local minimum. Are we looking for the x value or the y value when I ask you for the location? The x value. So at what x value do we have a local min? 3 pi fourths. Very good. Local mins occur in valleys. So at 3 pi fourths we have a local min. At negative pi fourths we have a local min. What is a relative maximum value? When I ask you for the relative max or the local max, is that a y value or an x value? It's a y value. Yeah, the local maximum value is negative 1.5. That's the y value at that high point. And that's why we call them local or relatives, because notice, in this case, the local minimum value is negative 0.5, and the local maximum is negative 1.5. And it's kind of weird that the local maximum value is higher than the local minimum value. But that's why we call them local. You zoom in so close that you don't even see the other stuff. And in that small, local, relatively small vicinity, it's the highest and lowest y value. Okay, so the last thing we want to do is go ahead and write an equation that's equivalent in terms of the cofunction. What's the cofunction of cosecant? Secant, yeah. So just like we did for sine and cosine, we wrote 3, one in terms of positive or negative of the other cofunction. We could do the same thing here with cosecant. We're just going to do one of them. You tell me, do you want to write a negative secant or a positive secant? It is goof-off day. Negative secant or positive cosecant? Blake Fain, you decide for us. Positive or negative? Negative. Good. I love the attitude. Negative. No, it's not an attitude. Negative 1/2. Negative 1/2. Good. Secant. And now, again, the only thing besides maybe the negative in front that's going to change is the horizontal shift. So the b value is still 2, and the a value is still negative 1. So we're going to have a parentheses 2, another parentheses, x plus or minus something minus 1. Now writing an equation for secant, positive or negative, or even a positive cosecant, would be exactly the same thing that you would do for writing sine and cosine. If we're doing a negative secant, kind of pretend that we're doing a negative cosine, right? A negative cosine, we're always looking for what? A high, an axis, or a low point? A low point. So where are the low points on our graph of cosecant? They're the points that are actually now the local maximums. Those are the ones that we turn downward. So for a negative secant, all we have to do is look for the top part of a branch that opens downward, which we have one at pi fourths and one over here at 5 pi fourths. This is where, if you need to, if you want to draw, like maybe connect with the light color, what the actual graph of sine or cosine would look like in between there, now it might be a little bit easier. Because if you're writing a negative secant, it's like writing a negative cosine, so you're looking for a low point on the yellow graph. But it's at pi fourths, so we could shift over to pi fourths. Minus pi fourths. No. Once you're writing an equivalent equation, you don't mess with the inside when you're creating the equation. It's just leave it as a 2. Now, because secant is an even function, would it be any different if I happen to throw a negative in front of the 2? No, that's the exact same graph. Because secant is an even function, this 2 could be positive or negative, and it would not affect the graph at all. What if I wanted a positive secant, just for kicks and giggles? What would I need to shift over to for a positive secant? Positive secant would be like a positive cosine. That would be starting at a pi point, which would be at, on the yellow graph, it'd be at 3 pi fourths. So for secant or cosecant, it's going to be where the graph is turned upwards. All right, very good. All right, any questions on A? Letter A. All right, what comes after A? Z, of course, much later. What comes immediately after A? B. Good, let's do B. Y equals 2, secant of negative pi halves x plus pi plus 1. So it's a secant function. Now, here's where you can make a careless mistake. Secant is what? Even, odd, or neither? It's an even. So we do have a negative b value here. The b value is negative pi halves. And we know for an even function, a negative b can simply become a positive b. You don't have to bring the negative up front. But you don't want to do it too early. If you just got rid of the negative there, you're going to be off on your horizontal shift because it's not in standard transformation form yet. So that's always your first order of business. Let's put it in the standard transformation form. 2 secant of, we factor out a negative pi halves from both terms. And of course, that's going to leave us a positive x. And when you factor out a negative from a positive pi, it first of all changes the sign, so it now becomes negative. And what are you left with when you factor out a pi halves from a pi? A 2. Because remember, factoring out is dividing out. And what is pi divided by pi halves? It's pi times 2 over pi, which is just 2. And of course, you quickly check before you proceed. What is negative pi halves times negative 2? Well, it's positive. The 2's divide out pi. Good. Got it. So notice you're actually shifting to the right 2 units. If you were to get rid of the negative first and then factor out, you would have a plus 2 there. You'd be shifting the wrong way. Now that it's in standard transformation form, that negative b value, because this is an even function, can just be thrown away. It does not change the sign out front. So it's a much easier task to sketch without a negative b. So now it's in standard transformation form, and to graph it, we're going to pretend that it is a what? Cosine. Yeah, so let's go ahead and write the information for the cosine equivalent. The amplitude would be 2. The absolute value of b would be pi halves. C would be right 2. D would be up 1. The period is 2 pi over b, which is 2 pi over pi halves, which of course simplifies to what? Stay, change, flip. Your pi's divide out. 2 times 2 is 4. Now, because there's a horizontal shift, you can either make a sacrificial axis or just think about it. We're kind of evolving, so maybe you don't have to do the rough draft anymore. Remember, for sine, cosine, cosecant, and secant, we count by what fraction of the period? A half or a fourth? A fourth, a quarter cycle. So if the period is 4, what's a fourth of 4? That's a half of 4. 4 divided by 4 is 1. We're counting by ones. 1 is a really nice number. So every critical value is 1 unit away. We're shifting the graph right 2 values. That's a multiple of the quarter cycle interval. So really, we don't have to make a sacrificial axis as long as we realize we're picking the graph up and we're moving it over 2 clicks to the right. We're setting it down 2 critical values over from where it started. All right, so the last thing I might think I'll do is do the range to help us set up the graph a little bit better. The D value is -1, and from there we go down to and up to the amplitude. So +1 minus 2 is -1, and then +1 plus 2 is 3. So that's the range for cosine, not the range for secant. But while we're here, can we get the range for secant? Do you need to graph it to get the range for secant? And if you know the range for its reciprocal cosine? If cosine is everything between -1 and 3, secant should be everything outside. So it should be -infinity to -1, and remember they share those values, union 3 to infinity. So it could be a multiple choice question. You don't have to sketch the whole entire graph to answer that question, as long as you realize how they're related. Okay, so let's go ahead and set up our graph. My y-axis is going to be right there. And most of my values are positive, so I'll draw my x-axis just a little bit lower than usual. And I'll go out the length of a cycle, which is 4, about 2/3 of the way. So there's 4, 2, 1. And so now I have 1, 2, 3, 4, 5, 6. I have room for another one. There's 0. Here's -1. There's -2. Now to set up the y-axis, -1 to 3, I'll call that -1. I'll call this 3 up here. That looks good. And then halfway in between there would be 1, somewhere in there. All right, so now I'm not going to, again, draw my new y-axis or my new sinusoidal axis. Here's what I'm going to know. I know that everything is moved to the right 2 units. Cosine normally starts at a high point, yes? So that would be at 0,3 without the horizontal phase shift. We are now moving the point 0,3, which is a high point, to the right 2 units. Okay, so the new y-axis would be at 2. But I don't have to draw it because I know what I'm doing now. I'm just going to put a high point at 2, 3. And of course, once you have a high point or a low point, everything else is predetermined. So if I go to the right then, I have an axis point at 3, 1, a low point at 4, -1, an axis point at 5, 1, and a high point at 6, 3. And then working back to the left, I have an axis point at 1, 1, a low point at 0, -1, an axis point at -1, 1, and a high point at -2, 3. So try to do it now without drawing all those temporary dotted lines. All right, so now the pretend is over. We're not going to pretend it's a cosine anymore because it's actually a secant. And so that just means we're going to do something different with these critical values. The axis points become vertical asymptotes. So again, always draw those first. So -1, 1, 3, and 5. High points stay high and turn up. Low points stay low and turn down. And you just draw them, make sure they stay in between the vertical asymptotes, but approaching them. And draw arrows on the end. So there you go. So once again, you can answer questions increasing, decreasing, local max, local min, all that good stuff. Now you can clearly see that the range is -infinity to -1, union 3 to infinity. So here's what we're going to do now. Last thing. Once we have the graph, we're going to write an equation in terms of the cofunction. The cofunction of secant is what? Cosecant, right. Either add the co or take the co away. And let's see, Jackie, do you want to do positive or negative cosecant? You decide. Positive. Okay, let's do positive cosecant. So we're going to come back up here to the standard transformation form for secant, and we're just going to change secant to cosecant. And then the only other thing that'll change is the phase shift of +2 or -2. So we're going to have y equals +2, because that's what she chose, cosecant, parentheses, pi halves, parentheses, x, plus or minus something, and then +1. So to write an equivalent graph for cosecant, you just kind of pretend you're doing it for positive sine. Remember, sine required looking at two things. Sine said we had to be on an axis heading up. So for us, the axis points are the vertical asymptotes, and heading up means that we have a branch that opens up. So where is there a vertical asymptote such that immediately to the right we have a branch opening up? 1 or 5, right? Those are the only two we have. So let's shift over to the first one. 1 to the right would be -1. Yeah. A negative cosecant would be on an axis heading down, which would be a vertical asymptote with a branch opening down immediately to the right, and that would be at 3. We don't want to go to 3 because we wanted a positive cosecant. All right, so pretty easy if you tap into the skills that you acquired doing sine and cosine. Questions on those? Fun, 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 or fun, 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 fun? The second one. Good. That's the right answer. Okay, so shifting gears here a little bit, looking at an application. There are lots of applications of sine and cosine. Lots. We didn't really look at that section other than the Friday before spring break, where you saw one application where you measured the height of the rider in the London Eye above ground at any given time. But there's not as many nice applications of tangent and cotangent, secant, cosecant, unfortunately. But here's a good one, all right? So let's look at this scenario. Look at the picture. It's beautiful. Doesn't that water look great? Yeah, until you realize there's a shark in there. A purple fin shark. Very rare, but very deadly. Okay, so we'll kind of stay out of the water here. You have a lighthouse on an island 3 miles off the shore, okay? And you know how lighthouses work, right? They house a light, and that light puts out a beacon. And it spins, okay? So this thing is spinning at a constant rate, which means it has a constant what velocity? Angular velocity. Good. Now, 3 miles offshore, perpendicularly, the orthogonal or the normal distance to the shore is the perpendicular. That's 3 miles. If we track the beam that's projected on the shore, and by the way, for matters of convenience, let's assume that the shore is perfectly straight and infinitely long in both directions. That's mighty convenient. Infinitely long in both directions. And also, let's assume that the light is also infinitely powerful so that I can actually project the beam on that shore, which means the light keeper is probably wearing protective eyewear and clothes, right? SPF 5000. What we want to do is track this beam as it projects along the shore. Assume that there's like a wall there or some mountains so that it has something to project upon. But we want to track the beam's distance along the shore from this perpendicular distance. So when the beam is shining right here, let me use yellow. Boom, if the beam is shining right there, we'll let the distance equal 0. And we'll correspond that with time equals 0. And if the light then house is, from our perspective, rotating clockwise, then the positive direction of the beam will be to the right, and the negative direction will be to the left. Okay? So here's what's essentially happening. The distance along the shore starts at 0. But as this thing rotates, the beam is going to project further down the shore to the right. And then the diagram that's shown, it projects some distance d down the shore. Now, as it continues to rotate, that beam is going to move further and further and further to the right down the shoreline. And it's still, all things considered, with an infinitely long shoreline and an infinitely powerful beam, you should be able to see it way down the end of the shoreline as this thing continues to rotate. But when will it disappear from the shoreline? When this thing has rotated through how many degrees? 90. As soon as it reaches 90 degrees, the beam now is shining parallel to the shore, out into nothing, and it's no longer projected on the shoreline. But up until 90 degrees, all things being ideal, it'll project somewhere down the line. So what would be the first angle before 90 degrees? 89.9999999. We can go on forever. Is there a first angle before 90 degrees? There's no such number. There's no first number before 90, real number. So what that means is, this thing, if you slow down the rotation, it can rotate infinitely close to 90 degrees without ever getting to 90 degrees. Would you agree? It can rotate infinitely close to 90 degrees without ever getting to 90 degrees. And as it approaches 90 degrees, what's happening to the distance d down the shore? It's getting bigger and bigger and bigger, approaching what? Infinity. There you go. So that's why we have to have an infinitely long shoreline and an infinitely powerful beam. So in theory, as it approaches 90 degrees, d is going to be approaching infinity. And as soon as it reaches 90 degrees, it just pops off the map. It's gone. Okay? Now, if we had another parallel shore on the opposite side here, 3 miles on the other side, it would then, once it gets past 90, it would pick up on the other shoreline down the line. But that's not what's happening here. It's projecting out into nothing. But once it gets past 270, what happens? The first number past 270 degrees is what? 270.0000. There is no first number. But immediately after it passes 270, it's now projecting on the shoreline where? Over here on the left, at negative infinity. And as it continues to rotate from 270 to 360, that beam is going to be approaching this again. So that's the weird idea. If you look at tangent, you might say, what in the real world, what in tarnation follows this type of behavior where the values increase forever to infinity, and then boom, they're just gone from the map in that very next instant. And in the very next instant, they just appear on the other side like some wormhole from negative infinity. Well, now we know. That beam is going to start at 0, and the distance down the shoreline is going to be increasing, approaching infinity. And when it reaches 90 degrees on its rotation, it disappears. But in the very next instant, it's shining on the opposite shoreline. If we had one on the other side, it would come from negative infinity and just appear out of nowhere. All right, so this is a nice example of an application of tangent. Now, one last thing before we get started. If the lighthouse is spinning with a constant angular velocity, and it is, if you read it, it says it's spinning at 2 minutes per rotation. That's a constant angular velocity. What do we know about the speed of the beam that's projected on the shoreline as it goes down the shoreline to the right? Is it constant, increasing, or decreasing? If you were to follow that projection along the shore with your eyeballs, would you move your head at a constant rate from left to right, or would you have to go like, whoa? You'd have to go whoa-ho, right? Because the speed of the beam as it projects along the shoreline is actually increasing, meaning its linear velocity is increasing. How do we know that? Well, remember that linear velocity is related to angular velocity by way of the what? We did the activity outside, remember? We added more people, which increased the what? The radius of rotation. This distance here, the hypotenuse, is your radius. And when it's up here at t equals 0, the radius is 3. But as it rotates, that hypotenuse is getting longer, which means the radius is getting longer. So it's having to travel a farther distance in the same amount of time, and the only way to do that is to speed up. That thing is moving very fast. You can simulate that on a small distance. If you turned out the lights in here and you had a flashlight, if you rotated from left to right at a constant rate, and you try to follow the beam along the wall, you would actually see that the beam on the wall is accelerating, okay, in the direction you're rotating. So anyway, there's the setup. Let's go ahead and read. A rotating light at the top of a lighthouse 3 miles away from the shore sends out a light beam in opposite directions. Pew, pew. As the beam rotates through an angle of theta, a spot of light moves along the shore. Let L be the length of the light beam from the lighthouse to this place on the shore. So it's not labeled here, but we're going to let that be L, which we just said is the radius of rotation. But let little d be the directed distance along the shore. So that's what we've already talked about. It's 0 when it's perpendicular, positive as it moves to the right, going to the right, and it's going to be a negative value when it's to the left. The beam is always moving to the right, so it's monotonic to the right. Blah, blah, blah. Assuming the lighthouse makes a full rotation every 2 minutes, so there's your angular velocity. Part A, sketch the graph of the function from 0 to 2 minutes. So what's nice about this is we're able to apply the graph of tangent to a real-life scenario. And on this axis, we're measuring the distance along the shore in miles as a function of time in minutes. And this is why we have to use radians on the x-axis. Radians are unitless. The ratios themselves that we're measuring on the y-axis are always unitless. When you have a unitless dimension on both axes, you can now put any units you want to the axes, like minutes and miles. All right? So let's go ahead and create our graph. Now, because this is a problem that we're conducting, we'll go ahead and start at t equals 0. We'll just like time it ourselves, all right? We'll get there when it's perfectly at d equals 0, and we'll start our stopwatch. So we don't need to sketch to the left. Now, when t is 0, what did we define as the basis, the distance along the shore? We're going to use that as our 0, okay? We're not measuring the distance from shore. We're measuring the distance it's traveled horizontally along the shore. So we're going to call that 0. So this one passes through the origin. It'll pass through the origin. Now we are measuring, let's go ahead and label the distance again in miles along the shore against time in minutes. So as this thing starts to rotate, the distance along the shore is going to increase, as we already mentioned. And then it's going to pop off the shore into nothingness when the angle of rotation reaches 90 degrees. Well, I'm not going to label this down here as 90 degrees, and I'm not going to label it as pi halves radians either, because what are we measuring on our axes? Time. So I need to come up here and figure out using the angular velocity, okay, how long is it going to take then for this lighthouse to rotate through 90 degrees if it makes a full rotation in 2 minutes? 30 seconds. Good. It's a fourth of that. 90 degrees is a fourth of a rotation. A fourth of 2 minutes is 30 seconds. But we want to count in minutes, so 30 seconds is how many minutes? 1/2 a minute. So you can call it 1/2, or I'm going to use decimals, 0.5. So at 30 seconds or a half a minute, it's reached 90 degrees, boom, and it's off the shore. Now extend your vertical asymptote. Now the next branch of tangent would come in from the bottom, boom, like that, and that would be the next critical value, which would be at 1 minute, and then it would increase to the right again, boom, and that would be 1.5 minutes, and then of course it would come in from the bottom, that would be 2 minutes, and then it would continue on again like that, da 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 da. I know it said to go to 2, but I always go above and beyond, so there's 2.5. So we have 2.5 branches of the graph of tangent sketched here. Now the graph of tangent, of course, would keep going forever and ever in both directions. But when we have applications, we need to look at a relevant domain. And what is relevant here? Well, when it starts, of course, it's projecting along the shoreline. The next branch, is this next branch from 1/2 minute to 1.5 minutes even relevant for this particular problem? What's happening from 1/2 minute to 1.5 minutes? That's going to be when the lighthouse is projecting its bulb out in this direction, right? Do we have a shoreline on the other side? No. So even though the tangent graph exists there, that next branch is not relevant for this particular problem. So you can erase it if you want. I'm just not going to highlight it. But at 1.5 minutes, it picks back up over here, and now it's shining on the shore for the next 30 seconds. So this next branch we want. And it'll do it again till 2.5 minutes, and then it jumps off the shore, and so the next branch we won't see. So for the relevant domain here, it's only every other cycle that measures the distance along that one shore. All right, does that make sense? It's on the shore for a full minute every other minute. Because for the second minute of its rotation, it's shining away from the shore into the ocean. All right, so that's what we're doing here. Okay, so now that we have the graph, let's go ahead. The next question says part B, write an equation for it. So let's do that. D of t instead of y equals is, well, let's see. We could do it in terms of tangent or cotangent. It would probably be easier to do it in terms of what? Tangent, right? Because it rotates clockwise, and we're measuring the positive distance to the right. That makes this function monotonic increasing, which is what tangent is. And do we need a phase shift for tangent if we choose tangent? Because tangent jumps right out of the origin, and that's what this one does. That's why we started our stopwatch there. Makes sense. So it's going to be tangent of, there's no phase shift, there's no vertical shift. So really, all we need, and I'm using t instead of x, we need to find the period. Because once we find the period, we can find the b value. So what is the period of our graph if the lighthouse makes one full rotation every 2 minutes? Is it 2 minutes? It's just one. Very good. Because remember, once around the lighthouse is like once around the unit circle. And tangent and cotangent make 2 full cycles once around the unit circle. So that would make 2 full cycles once around the lighthouse. So remember, the period of tangent is just going to be between the vertical asymptotes. And from 1.5 to 2.5 is a minute. So the period is 1 minute, which means the b value that goes in the equation is, first of all, what over b? Pi or 2 pi? For tangent and cotangent? Pi. Tangent and cotangent are pi. So it's pi over 1. What's pi over 1? Pi. So the b value is pi. And now for the a value, I know it's going to be positive, but is it just 1? Or is it 2? Or is it 3? Or is it 5? Or is it a half? How can we determine what the a value is? Well, that's a good question. There's a number we haven't used quite yet. The fact that the lighthouse is 3 miles off the shore. If you were measuring the distance d, it's always going to be a Pythagorean theorem. And 3 ends up being the short leg of one of the right triangles, okay, depending on how far you are. D is one of the legs, and L is the hypotenuse. So if you were to find the distance d, it would require the number 3. And so 3, as it turns out, ends up being your value of a. So anytime you have a distance off the shore of whatever, a miles, that's going to be your a value in your equation. So there it is. We now have a working equation that for values of t that make sense, we can predict then how far down the shore this light beam is. And so that's the next part. It says find d of a sixth, d of a fourth, and d of a third. I'm not going to do all of them, but let's go ahead and do d of 1/6. Notation is everything. Now that's a sixth of a minute. 1/6 of a minute is how many seconds? 10 seconds. So basically, this thing's rotating pretty slowly. We're waiting for 10 seconds to go by, and we want to see, okay, after 10 seconds, how far has it been projected down the shoreline from the perpendicular distance? Well, we just plug it in. We get 3 tangent of 1/6 times pi is pi 6. And now we don't need no stinking calculator because we got one in our head. What is tangent of pi 6? I know you're just bashful. You don't want to show off. Not that you don't know. It's the square root of 3 over 3, right? Which now when you multiply by 3, you get just the square root of 3. And that would be units of miles. Now the square root of 3 is about 1.7. So there you go. After only 10 seconds, it is already 1.7 miles down the shore. So if you watch it with your eyeball for 10 seconds, you're going to be looking a little more than a mile and a half down the shore. Do you think you could keep up with it if you were on the shoreline? You think you can keep up with the light as it moves along the shore? Can you move 1.7 miles in only 10 seconds? That's fast. In fact, let us see how fast that light beam is traveling down the shore at that moment. In other words, let's figure out its linear velocity. Well, linear velocity v, let's just measure it in miles per hour. So you can just do this by stoichiometry. We know it travels the square root of 3 miles in how many minutes? 1/6 of a minute. Well, we don't want to do miles per minute. So let's just convert then minutes to hours. 60 minutes in 1 hour. Your minutes divide out and you're left with miles per hour. Now 60 divided by 1/6, is that 10? 60 divided by 1/6, is that 10? No, that's 60 times the 6. Say change flip, you get 60 times 6, which is 360 times the square root of 3 mph. And if you're curious what that is, I will calculate it for you. That is pretty fast. 360 times the square root of 3. At that moment, it's moving 623.538 miles per hour. That's fast. Now, this is kind of getting into calculus because we said already that the speed is increasing. That speed is only good at that moment. In the very next instant, that speed should be what? Bigger or smaller than that? Bigger. It's accelerating down the coastline. All right? So let's do the next one here. Let's do d of 1/3. Let's just see what that is. So d of 1/3 is going to be 3 times tangent of pi thirds. And of course, what's pi thirds? Tangent of pi thirds? It's just square root of 3. So now it's 3 square root of 3 miles down the coast. And let's figure out the velocity of the beam. It's going to be in miles per hour. So it's 3 square root of 3 miles. This time in only 1/3 of a minute. So if you multiply by 60 minutes over 1 hour to convert your units, you get 180. 60 times 1/3 is 180. Times 3 gives you 540 times the square root of 3. And that's miles per hour. And 540 times the square root of 3 is 935.307 miles per hour. Wow. If there were light police on the shore, if they could catch this guy, they'd probably give him a speeding ticket. So that's interesting. Not only is our coastline infinitely long and the beam infinitely bright, but the speed of the beam down the coastline is also approaching what? Infinity. And believe it or not, infinity is faster than the speed of light. But how could that be then? If a beam of light, can a beam of light travel faster than the speed of light? Oh my gosh. These are some of the things that some people considered over spring break. Okay, when you're on a beach having fun, these are the types of questions that can enhance the fun in a safe way. All right. Thank you. Yeah, tomorrow we'll finish the section pretty easily. The worksheet's going to be due on Friday, and we will quiz on Friday. Good luck tomorrow, band, and pre-UIL.